This is Algebra 2, Unit 12, Lesson 5 on independent and dependent events. Now, in the previous lesson's homework, we saw how the occurrence of one event could change the probability of another event. When this happens, we say the two events are dependent on each other. When the occurrence of one event has no effect on the probability of the other happening, those are independent. So if one event affects another, it's dependent. If one event doesn't affect the other, it's independent. So let's see if we can classify whether these events are dependent or independent. A person pulls a red marble out of a bag that has 5 blue and 7 red marbles and does not replace it. So basically they pull a marble out of the bag and then doesn't put it back. Then a person pulls another red marble. Is the probability of pulling the second red marble out dependent on pulling the first red marble? Yes, it would be. Because if a red marble is pulled first, is pulled on the first try, it will change the probability of pulling a second one. So, for example, if you are pulling a red marble on the first try, there's a 7 out of 12. But if you get a red marble, there's not 7 red marbles anymore. There would only be 6. So the probability will be affected. So the one pull does affect the other because you did not replace it. If you had put the marble back in, the probability wouldn't have been affected. All right, now, a person flips a coin and notes that it comes up heads. Then the person rolls a standard 6-sided die and notes that it comes up as a number less than 3. Is the probability that the number came up less than 3 dependent on getting a head when flipping the coin? Well, does it matter rolling a number? Does flipping a coin affect that? No. Okay, because the two events are independent. Okay, flipping a coin does not affect rolling a die. So if you roll a die or flip a coin, one has nothing to do with the other. So your probabilities are not going to be affected. So you have to be very careful of whether events are dependent or independent. Does one probability affect the other probability? Now, the idea of independence is one that comes fairly naturally, but it is important in order to see that there are associations among two events. Let's develop a tool to test dependence. The spinner below is spun once and its outcome is noted. Let E be the event of getting an even, P be the event of getting a prime, and L be the event of getting a number less than 5. So let's find the following probabilities. All right, what is the probability of getting an even number? Well, probability of getting an even number, there are 4 even numbers, 2, 4, 6, and 8, out of a total of 8 on the whole spinner. So that's going to be 1/2. All right. Let's figure out the probability of getting even given the outcome was a prime number. So even given prime, so P of E given P would be E and P out of P. That's what given means. All right, so what does E and P mean? Well, even and prime. How many numbers are both even and prime? Well, 2 is the only even number that is also a prime, so there's 1 of there. And how many prime numbers are there? Well, there is 2, 3, 5, and 7 are all prime. So this probability is going to be 1/4. All right, the probability of getting an even given the outcome was a number less than 5. In other words, P of E given L. Well, P of E given L would be E and L out of L. All right, so how many numbers are even and less than 5? All right, well, even and less than 5 would be 2 and 4. So there's 2 of them. And how many are less than 5? 1, 2, 3, 4. 2 out of 4 is 1/2. Okay, so which event does E depend on, P or L, and how can you tell, and what is a reasonable test? Well, if we look at our probabilities here, we had E given P, and E given L. All right, so which one depends on the other? Well, it would have to be this one, because E depends on P. How can we tell? Because the probability changed. when we did E given P, the probability changed to 1/4. We did E given L, the probability didn't change. All right, so E depends on P because the probability changed. When P occurred. All right, so occurred when P occurred. But it didn't change when L occurred. All right, so when we did the probability E given L, the probability stayed 1/2. When it was E given P, the probability changed to 1/4. So that means E and L are independent. The probabilities didn't change when we were changing the values there, but it did change when we were using P. So E and L are actually independent events. All right, so the definition of independent events says, two events, A and B, are defined to be independent of another if P of A given B equals P of A, and likewise if P of B given A equals P of B. So, let's take a look at this example. A survey of 57 sixth graders was done to determine what subject was their favorite. The results are shown in the table below, sorted by gender. Okay, so does it appear based on the data in the table that the preference for math as a favorite subject has dependence on a student's gender? Show the analysis and explain your findings. Okay, so we want to look at the preference of math. All right, so what is the preference just overall of liking math? All right, well, the probability of liking math, there are 18 out of a total of 57. Okay, so the definition of independence says, two events, A and B, are defined to be independent of another if P of A given B is P of A, and P of B given A is P of B. So basically, if you do the probabilities of the event and given the other event, then the probabilities will be the same. All right, let's try this out. It's a little more clear when you see it actually demonstrated. A survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. So here is your table. Does it appear, based on the data in this table, that the preference for math as a favorite subject has dependence on a student's gender? All right, show the analysis and explain your findings. Okay, so we want to compare the probability of liking math to the probability of liking math when you're male, given that you're male, and the probability of liking math given that you're female. All right, so let's take a look at the individual probabilities. All right, so first of all, what is the probability that you like math? All right, well, from this survey, how many people like math? Well, that would be 18 total. Out of how many total in the group? Well, there's a total of 57. All right, so 18 out of 57, I did right here, is about 0.32. So 18 out of 57 is approximately 0.32. That's your probability. All right, let's figure out now the probability that you like math if you're male. Okay, so remember, math given male means the probability that you like math and male, or numbered like math and male, out of the total that are male. Okay, so math and male, well, that would be 10. Out of the total number of males, which would be 27. All right, so 10 out of 27 is approximately 0.37. All right, so that's approximately 0.37. Okay, and the probability of math given that you're female would be math and female out of female. All right, so looking at our chart, math and female would be 8 out of the total number of female, which would be 30. And then go to my calculator, 8 divided by 30 is about 0.27. Okay, so let's take a look at our probabilities. Did our probabilities change? Yeah, they did. So it appears that these results are slightly dependent on gender. So it appears there is a dependence based on gender. For liking math. So you can see that the probabilities are not equal. The probabilities change. So they are not, the probabilities are not equal to the overall probability of liking math. Okay, so when we threw in the gender, you can see the probabilities change. When the overall probability is 0.32, this one's 0.37, this is 0.27. So the probability did change when we added the fact that you had males and females out of the group. So you can see that one is slightly dependent. All right, so let's try social studies. Does it appear, based on the data in this table, that the preference for social studies as a favorite subject has depends on the student's gender? So let's look at the analysis. All right, so we're looking at the probability of social studies, liking social studies, the probability of liking social studies given that you're male, and the probability of liking social studies given that you're female. Okay, the probability of liking social studies. So if I flip back to my table here, liking social studies, there are 19 out of 57. Okay, so that's 19 out of 57. And I believe that's 1/3 if I work that out. 19 out of 57 is 0.333. Math enter is 1/3. I happen to know 0.33 is a repeating decimal, so okay, is 1/3. Or 0.33 if you want to work it that way. Okay, probability of liking social studies if you're male. Remember that is social studies and male out of number of social studies. Okay, so social studies and male. Social studies and male would be 9 out of the total social studies would be, or total number of male, I'm sorry, 9 out of 27. Okay, and that's 9 out of 27. That's also 1/3 or 0.33. All right, and then social studies and female would be social studies given female would be social studies and female out of the total number of females. So social studies and female would be 10 out of the total number of female would be 30, which is also 1/3 or 0.33. Okay, so what happened with the probabilities? Well, that means liking social studies and the favorite subject has no dependence. So, like social studies and gender, I'm sorry, has no dependence. These events are independent. Okay, because the probabilities are the same. Okay, the probabilities of the events are independent. The probabilities did not change based on the gender. Gender did not change the probabilities. So there is no dependence on gender to prefer social studies. Okay, so the probabilities stayed the same when we threw in the gender. Okay, so there is a nice test for dependence that can be applied easily and comes from our formula for conditional probability from the last lesson. All right, we'll save this for class the next day. So we want to figure out independent and dependent events. You have to see if the probabilities changed given different conditions.